plus ion is surrounded by 6 ammonia molecules. Located at the vertices of an octahedron, while the 3 Cl- ions are dissociated as free ions. Werner's proposition is based upon his extensive experimental work with complex compounds of cobalt-3 chloride and ammonia. Werner prepared different compounds composed of cobalt-3 chloride and ammonia, all of which had different colors and were thus named accordingly. Note here that these are not the present-day IUPAC names of these compounds. All these compounds contain ammonia, and thus he reasoned out that just like ammonia gets dissolved in dilute hydrochloric acid to form ammonium chloride, aqueous solutions of these compounds must react with dilute hydrochloric acid to form ammonium ions in solution. However, to his surprise, he found that none of these compounds reacted with HCl even at very high temperatures. Based on this observation, Werner proposed that ammonia molecules are bound very tightly to the central cobalt ion and cannot be released as ammonium ions readily. Next, Werner tested all his solutions for the presence of chloride ions. As we already know, when a solution containing chloride ions is reacted with excess of Ag plus ions, the chloride ions precipitate out as AgCl. Accordingly, Werner reacted all the 4 compounds with silver nitrate and analyzed the results quantitatively. He found that while 3 moles of chloride ions were precipitated for 1 mole of COCl3 6NH3, 2 moles of chloride ions precipitated from COCl3 5NH3, while only 1 mole of chloride ion precipitated out from COCl3 4NH3. This led him to the conclusion that not all chloride ions bound to the central metal ion are ionizable. Only those ions which are ionizable precipitate out as silver chloride. Werner named these valences as primary valences. Werner called the parts of the molecule which were not ionizable and were held strongly to the central ion by coordinate bonds as the secondary valences. The words primary and secondary, however, no longer bear the same importance. In the present context, primary valence is equal to the oxidation number of the central metal ion in the complex, while secondary valence is equal to its coordination number. Werner's theory also throws light on the structure of these complexes. while the primary valences are non-directional. Secondary valences to the metal have characteristic spatial arrangements, and this arrangement assigns a specific geometry to the coordination compound. Accordingly, he postulated each of these complexes as octahedral. Summary. According to the Werner's theory, the central metal ion in coordination complexes possesses two kinds of valences: primary valences, which are ionizable, and secondary valences, which are non-ionizable. Primary valences are non-directional, while secondary valences impart a specific geometry to the complex. Coordination number and geometry of complexes. The transition metal ions are capable of forming coordinate complexes. The total number of ligands attached to the central metal ion determines the coordination number of that ion. The coordination number is one of the factors affecting the geometries of the complexes. The coordination numbers 4 and 6 are the most common coordination numbers for complexes of transition metal ions. Let's study the geometries of complexes with coordination number 4. Two geometries are found in the complexes of metal ions with coordination number 4: tetrahedral and square planar. Tetrahedral complexes. A tetrahedral geometry is more common in complexes with coordination number 4. Tetracarbonyl nickel is one of the complexes having tetrahedral geometry. Square planar complexes. This type of geometry is exclusively found in metal ions having 8 electrons in their d orbital, such as nickel. Tetracyanonickelate is one such complex. As we can see, although both these complexes possess the coordination number 4, they exhibit different geometries. Now, let us see the geometries of complexes with coordination number 6. Two different geometries are possible in these complexes. Octahedral. The most common is the octahedral geometry. Almost all hexa-aqua ions, such as hexa-aqua copper, show this geometry. Trigonal prismatic. It is found in the compounds having 3 bidentate ligands, such as oxalates. In spite of having the same coordination number of 6, all the complexes show different geometries. Summary. We've studied that the total number of ligands attached to the central metal ion determines the coordination number of that ion. We've also studied the geometries of complexes with coordination numbers 4 and 6. Geometry of K4FeCN6 based on its magnetic property. Potassium ferrocyanide is a common laboratory reagent used to detect copper ions during qualitative analysis of salts. In the potassium ferrocyanide complex, the ion atom Fe is in the +2 oxidation state and is coordinated with 6 Cn- ligands. Thus, the coordination number of Fe2+ in this complex is 6. We have studied that such a complex with coordination number 6 can have either D2sp3 or sp3d2 states of hybridization. In this topic, we will study how to predict the state of hybridization of a complex depending on its magnetic property. Let us first consider the possibility of D2sp3 state of hybridization. The electronic configuration of Fe2+ is Ar3d6. The 6 electrons are distributed in 3d orbitals as shown. For D2sp3 hybridization, the Fe2+ ion should possess 2 empty 3d orbitals. The strong Cn- ligands force the 6 electrons to pair up and occupy 3 of the 3d orbitals. The 2 vacant 3d orbitals thus formed undergo hybridization with the vacant 4s and 3 4p orbitals. This results in the formation of 6 equi-energic D2sp3 hybrid orbitals, which can accommodate the 6 electron pairs donated by the Cn- ligands. The FeCN6 4- ion thus formed is octahedral. Since all the electrons in the complex are paired, it is diamagnetic. Now, let us explore the second possibility of sp3d2 state of hybridization. For this, no rearrangement of the 3d electrons is necessary, since the orbitals of Fe2+ required for this hybridization are already unoccupied. These 6 sp3d2 hybrid orbitals can accept the electron pairs donated by the 6 Cn- ions. The complex shall still have octahedral geometry, but as there are 4 unpaired 3d electrons, it will now be a paramagnetic complex. It has been found that FeCN6 4- is diamagnetic. Thus, it involves D2sp3 hybridization, and its geometry is octahedral. Geometry of K3FeCN6. In the potassium ferricyanide complex, Fe3+ ion coordinates with 6 cyanide ligands. The outer electronic configuration of Fe3+ ion is Ar3d5. These 5 electrons occupy each of the 5 3d orbitals singly. As the complex is octahedral, the Fe3+ ion can be either sp3d2 or D2sp3 hybridized. Let's first consider D2sp3 hybridization of Fe3+, for which it requires 2 empty 3d orbitals. This necessitates the rearrangement of the 5 3d electrons. The strong Cn- ligands can force the 3d electrons to pair up to achieve this arrangement. The 2 3d orbitals thus made available along with the 4s and 3 4p orbitals that are unoccupied undergo D2sp3 hybridization to form 6 equi-energic D2sp3 hybrid orbitals, in which 6 electron pairs donated by 6 Cn- ions can be accommodated. Since there is one unpaired electron, the complex is paramagnetic. The experimental value of magnetic moment for this complex is about 1.80 Bohr magnetons. This is in agreement with the theoretical value of the magnetic moment of a complex having one unpaired electron. Now, if the Fe3+ ion undergoes sp3d2 hybridization, there is no need for rearranging the 5 electrons of the 3d orbital. Hence, 1 4s orbital, 3 4p orbitals and 2 4d orbitals take part in hybridization. Six equienergic sp3d2 hybrid orbitals thus formed accept electrons from the 6 Cn- ligands. The complex so formed has 5 unpaired electrons and is thus strongly paramagnetic with a magnetic moment of about 5.92 Bohr magnetons, which is not in agreement with the experimental value of about 1.80 Bohr magnetons for this complex. Thus, the K3FeCN6 complex is octahedral, has D2sp3 hybridization of the central Fe3+ ion, and is paramagnetic with a magnetic moment of 1.80 Bohr magnetons. Geometry of FeH2O6 3+. An aqueous solution of ferric chloride contains an aqua complex in which 6 H2O molecules are attached to the Fe3+ ion by coordinate covalent bonds. The experimental value of the magnetic moment of this octahedral complex is about 5.96 Bohr magnetons. The theoretical value of the magnetic moment of a complex having 5 unpaired electrons is 5.92 Bohr magnetons. This proves that the inner 3d orbitals are not disturbed by the relatively weak H2O ligand. The complex ion FeH2O6 3+ acquires an octahedral geometry by sp3d2 hybridization. In contrast to this, in FeCN6 3- complex, the Cn- ligands, which are stronger, force the 5 3d electrons to rearrange in order to facilitate D2sp3 hybridization. Thus, whether a D2sp3 or an sp3d2 hybridization shall occur in an octahedral complex ion is determined by the strength of the ligands. Homoleptic and heteroleptic complexes. A compound in which a central metal atom or ion is bonded to several surrounding ions or molecules called ligands by coordinate covalent bonds is called a coordination compound or complex. Let us add water to this salt to prepare a solution. The complex ionizes as pentaamine bromo-cobalt 2+ and sulfate 2- ions in the given solution. Now add some aqueous barium chloride to this solution. The sulfate ions in solution react with barium chloride to form barium sulfate, which is seen as a white precipitate. This confirms the presence of sulfate ions in solution. These ionizable sulfate ions of the complex are called counter ions. While CONH3 5Br2+, an ion composed of the central metal ion and its ligands, is referred to as the coordination sphere which is denoted by square brackets in the complex. On similar grounds, complex CONH35SO4Br, in which the coordination sphere is CONH35SO4 plus and Br minus are the counter ions, will ionize as CONH35SO4 plus and Br minus ions respectively. Bearing in mind the coordination sphere of a complex, we can designate any complex as homoleptic or heteroleptic. For example, in pentaamine sulfato-cobalt 3 ion, both ammonia molecules as well as sulfate ions donate an electron pair each to the central cobalt ion. Such complexes in which more than one kind of donor groups are attached to the central metal ion are called heteroleptic complexes. However, in hexa-aqua cobalt 3 ion, water is the only donor group attached to the cobalt ion. Such complexes in which only one kind of donor group is attached to the central metal ion are called homoleptic complexes. To sum up, in a coordination compound, a central metal ion is attached to ligands by coordinate covalent bonds. A complex compound ionizes into counter ions and coordination sphere. If all ligands attached to the central metal ion are same, the complex is homoleptic. However, if more than one kind of ligands are attached to the central metal ion, the complex is heteroleptic. Geometrical and optical isomerism in complex compounds. Compounds having the same molecular formula but differing in the spatial arrangement of their functional groups or atoms are called geometrical isomers, and the phenomenon is called geometrical isomerism. Geometrical isomerism is generally found in complexes with coordination numbers 4 and 6. Let's begin with complexes having coordination number 4. Such complexes may have either tetrahedral or square planar geometries. In tetrahedral complexes, all the 4 ligands are equidistant to one another. Hence, geometrical isomerism is not possible. However, square planar complexes do exhibit geometrical isomerism. Consider the Ma2B2 type of a complex. Here, M denotes the central metal ion, while A and B denote unidentate ligands. Both the A ligands are present at adjacent positions, and so is the case with B ligands as well. This isomer is named as the cis isomer. Another orientation of the same molecule is possible in which identical ligands are placed opposite to each other. The complex is designated as the trans isomer. Cis D-amine D-chloroplatinum 2 and trans D-amine D-chloroplatinum 2 are the respective examples. Another square planar complex is of the type MABCD. It has 3 possible orientations. In 2 of these orientations, the ligands A and B are placed adjacent to each other, and in the third one, they are placed opposite to each other. Accordingly, these isomers are designated as cis and trans forms. There are 3 possible isomers for this compound: 2 cis and 1 trans. Quite obviously, square planar complexes of the type Ma4, Ma3b